x. Well, let's hold 17 until Lena's turned hers in. We'll happily do it. Yeah. Yeah, no worries. What else do you guys have before that? Beck. Yeah, 59's a pain too. Mostly just because the because of the algebra at the end. All right. So first things first, what is all that stuff in there for? Well, why do we need that?
For solving where your answers in between. Oh, no. I mean, if you need a positive or a negative.
All it's going to do is ensure that cosine inverse, like that this function is defined for all values, like it'll be defined all the time, because cosine inverse is only defined from -1 to +1, correct? By restricting our value of x and our values of a and b in this way, it's ensuring that the result here is going to be between -1 and +1, so that this function is defined all the time, so you don't have to make any special allowances when taking the derivative. Because if we're taking the derivative of a function and it's like not defined anywhere, or if it's not continuous, like we have like this is no longer a trivial task where we're just applying our derivative rules. It's a much more complicated problem. That's all this is doing, is ensuring that it's continuous over its domain and differentiable over its domain, basically. Okay? So when I look at this, this is an obvious chain rule to start, right? So I'm going to use the arc cosine function, which is -1 over the square root of 1 minus x squared, but the x in this case is that big gross looking fraction. So that's the derivative of the outside. And then the derivative of the inside is just going to be the derivative of that big gross looking fraction. So to do that, I need to use a quotient rule.
How did you find that outside?
That's the derivative rule for inverse cosine. The derivative rule for inverse cosine is -1 over the square root of 1 minus x squared. But the x squared in this case is the insides. So it's that big fraction. Okay, so the quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom Now, if I distribute these through, I'd have -a squared sine squared, just sine x, minus ab cosine x sine x. And then here I'd have -b squared, but I have that negative sign in front of it, so it's really plus. and I'd have a minus 2ab cosine x sine x, but I have a negative in front of it, so that's really plus.
Wait, isn't it negative or b squared sin x?
Oh, thank you. Sure. And then I have, yeah, so that's that. I noticed that, hey, those guys can cancel out, and that's nice. And if I look at the denominator down here, what I'm going to do is I'm going to multiply it into the denominator in the other fraction. To do that, though, it needs to have a square root around it. So instead of thinking about this as something squared, I'm going to think about it as the square root of that thing to the fourth. That'll allow me to multiply it inside of the square root. So it'll multiply in there and in there. And I notice when I multiply to the fraction, that the fraction is going to reduce and clear that fraction inside of a fraction out of there. Everybody's okay with that? And I guess as long as we're at it, I'm going to distribute this -1 up to that stuff. So I'm doing all this simplifying in kind of one step so as to not have to write down like a million trillion things. And actually, I'm going to factor the sign out of there too. Everybody's okay there? All right, so what do we have now? We're going to have an a plus b cosine x to the fourth minus an b plus a cosine x squared times the a plus b cosine x squared. If I look at the denominator, I see that I have a greatest common factor of an a plus b cosine x squared, which when I factor it out and do the square root of it, I can just write that as a plus b cosine x regular. Everybody's okay there? What's up, Elena? Huh? Oh, I didn't mean to. Thank you. So what I have left is an a plus b cosine squared here, because I factored one of them out. So if I FOIL that out, I have one of those. And then I have a b plus a cosine squared that I'm minusing. So when I FOIL that out, I get that. Those guys cancel. Oh, sure. I just forgot the 2. Yep. And now, if I do a little factor by grouping, if I take that piece, I can take a 1 out of there, and I take these pieces, I guess that's supposed to be cosine squared, and take a cosine squared out of there, or a negative cosine squared. Oops. And sorry, that's not supposed to be a plus there. It's supposed to be the square root. That's all still under the square root. If I finish factoring that out, I can factor that by grouping. So here I'm going to reduce. Remember the a squared minus b squared in the denominator is underneath the square root. So it has an exponent of 1/2. So when I reduce it from the numerator, that makes the numerator's exponent 1/2. That's why I just put a square root on it to reduce it. And 1 minus sine squared is, or 1 minus cosine squared is sine squared. And because, again, that's underneath a radical, I can reduce that with the sine x. And so what I'm left with here, I think, is just this. Is that the back of the book? Did anybody look this up? If it's not, I'm going to be kind of sad because there's a lot of work to get to there.
Yeah, that's right.
Makes me feel good about myself when I can do that fresh and not make any mistake along the way. Now, to remind you guys, where was the calculus done at?
A while ago.
Was back at this step where the calculus was done, right? Like on a test setting, you could stop there if this is a free response question. Now, if this is a multiple choice question, very unlikely you could look at that and the multiple choice answers that looked like that and be able to tell which one is right and which one is wrong without actually burning through the simplification. But if it's not a multiple choice question, you don't need to simplify that for either me or the AP unless it asks to say, show that this derivative is equal to this, right? That would be the only kind of instruction that would require you to do the simplification. I mean, I did lots of stuff on lots of steps because of the simplification. Yeah, I did.
I was just looking at like the calculus part.
Oh, well, like
You didn't follow when I go back.
this was just like, I did a chain, right? That's just the chain rule. And then this, I just did the quotient.
That was it.
And that was it for the calculus. It's just a chain rule, then a quotient rule. And I just needed the quotient rule to do the derivative of the insides. And after that, the calculus was done. Just a lot of like algebra. That I did like lots of tricky simplification stuff, like looking for things to cancel or like simplifying stuff down. It just gets yucky. You know, the trick is like look for stuff to factor before you start foiling things out, right? Braden? Yes.
Do we have like
Uh-huh. Well, this was just the derivative rule, right?
Oh.
So I'm just used this one. Is that something you need to memorize?
Yes.
Yes.
If you were to like forget that one, hypothetically, like there's no other way you can do the problem.
Other than like the derivation, you'd have to derive the inverse cosine formula, and we skipped the proof for that, so unlikely you'd be able to come up with that on your own. So that's a need to have it memorized kind of situation. I was going to do 17 if there wasn't follow-ups to 59, because we had asked about that, and I'd put off that for a minute. Yeah, okay.
Or do you want to do 17?
Is it about 59?
No.
Okay, let's do 17 first, and then, because that was the first question somebody asked about, and I put it on pause because you were doing 17 while they asked about it, and I didn't want to spoil the suspense for you. Okay. So if I look at this as an implicit differentiation problem, the left-hand side requires a chain rule to start, right? Because I have the tan inverse of something. What's the derivative formula for tan inverse?
Over one.
Yeah, 1 over 1 plus inside squared. So there's my inside, 1 over 1 plus the inside squareds. And then I have the derivative of the inside. Everybody's okay so far? Okay. The derivative of x is 1. To do the derivative of x plus y squared, need a product rule. So I'll do the derivative of x times y squared plus x times the derivative of y squared, which is 2y dy dx. Everybody's okay? Now let's go back and do the derivative of x squared y. Oops. Again, to do that, I need to use, okay, derivative of x squared is, okay, and then the derivative of y is dy dx. I'm going to skip writing the 1. Everybody's okay with that? You guys did it, so I figured it must be okay to do that. Do a little bit of simplification as I write stuff down. So my goal now is to get the dx dy's by themselves on one side and everything without a dy dx attached to it to the other side. So I'm going to distribute that through. That's going to give me an x squared 1 plus x to the 4th y squared dy dx. And then I'm going to subtract over the 2xy dy dx. And I'm going to subtract over the 2xy over 1 plus yada, yada, yada. Bless you. So far, so good. I'm going to factor off my dy dx and divide both sides by x squared over 1 plus x to the 4th y squared minus 2xy. And at this point, you could be done. Now, this isn't what the back of the book's going to have, but the calculus is done. The dy dx is by itself. From here, it's just going to be algebra cleanups. If I were so inclined to try to clean this up, what would I do to do that? I would multiply both sides, or I'm sorry, the top and the bottom, by 1 plus x to the 4th y squared. That'll clear out the fraction inside of the fraction. So when I multiply to here, I could write that as a FOIL problem where I could just, think about it multiplying to 3 pieces. So I would do that. Probably multiplying to 3 separate pieces will make the multiplication easier. And I think, It's probably as good as we can do, right?
Yeah, that's,
That's what the back of the book has, is something similar to this?
yeah,
Okay. So that seems okay. I was trying to see if there's any other sneaky factoring I can do, like the common factor of x in the denominator, but not in the numerator. It didn't look like there was going to be anything good, but I'd have looked at it for a minute to see. I hate the 5 terms in the numerator, though. That makes the factoring much harder. If there was any like factor by grouping to do, can't really do it with an odd number of terms like that. Pierce. Okay, sure.
And the product rule at the very beginning, why doesn't the dy over d of x stay with the x and it's 2y?
Because it's only multiplied to this stuff. Because when I did the product, rule here, this is my, like, if that's my f and that's my g, that's the derivative of the f times g. So no y got differentiated there. And then it's f, and then it's the derivative of g. So you just have that dy dx multiplied to the f and the other parts of the derivative of g. So this is just like 3 things multiplied together. So x times 2y is just 2xy, and then times dy dx is just 2xy times dy dx.
How do you like does it always go? Or like if you do the product rule, it's always up to the second half of it? Or like,
It depends on where the y is, right? The y was our g part. So only when I do the derivative of g am I going to generate a dy dx, because that's the only time when I'm doing that product rule that I'm differentiating a y.
okay.
Is that?
Yeah.
Because up here, it's just g. I didn't do any differentiating to y, so there's no dy dx. The y, we just have a y in it. Is that?
Yeah, I know that's good.
Okay. All right, and Pierce, you said 29?
Yeah.
Okay. Okay, so this one says it wants you to find the equation for the tangent line to the curve at that point. It's pointing out that this specific equation is a type of, I think they're Limason curves, if you remember back from trig and pre-calc, that it's that type of Limason curve is called a cardioid because it kind of looks like a heart. Yes.
So for like all those problems, it was like 25 through 31. It gave you like those graphs. Like, does that play any effect?
None whatsoever to me, other than like that's going to be my tangent line, right? So I can tell the slope should be a positive number. You know, that it's not going to be like 57 or something. Like it's going to be something relatively small.
Okay.
It can give me some intuition as to whether the answer I got for the slope was going to be correct or not. But that's the only thing that I'd be using, you know. Is that okay?
Yeah.
All right. So we'll take the derivative of both sides. Derivative of x squared is? Derivative of y squared is? 2y dy dx. To do this, I'm going to do this as a chain rule. So 2, and then the insides. Now to the first, times the derivative of the inside. So the derivative of 2x squared is, and the derivative of 2y squared is, and the derivative of x is, oops, forgot the plus sign there, and then, because x, like z squared or something is the outside function. Okay. So now it's a simplification game trying to get the dy dx by itself, which yuckarooskies. Do I have to?
Still count as calculus, trying to get it alone.
Yes, because I guess here's the other option. We don't really need to know the closed form for the derivative, right? We just need to solve for dy dx when x is 0 and y is 1/2. So we can plug it in right now. Yeah. And then just get the dy dx by itself when everything is a number. How does that sound to you guys? You like that better?
Way better.
Okay. All right, so let's see. 0, 0, 0, 0. So 2 times 1/2 is just 1. And then 1/2 squared is 1/4 times 2 is 1/2. And then 4 times 1/2 is 2. So 2 times 1/2 is just 1. So if I subtract this dy dx over and then add this 1 over,
Where did that dy dx come from?
this dy dx is this one, and this dy dx is that one.
Oh, okay. So you simplified it.
So my slope is 1. So y minus y1 equals m times x minus x1, or just that this is y equals x plus 1/2. That was probably easier than getting the derivative separated. I guess if I don't need to do that, why do it, right? Like we plug these values for x and y in after the calculus is done, and it's fine. Of course.
Why don't you just subtract dy from the right side? Because there's 2.
Because I had one of them here, and I have 2 of them there. So if I subtract, so I didn't get a negative sign, basically, right? You could have done it to the other way and subtracted 2 dyx's over, and then you have negative dy dx equals -1. By doing it the opposite way, I avoided having to divide by a negative at the end. Whoop-de-doo-doo. But if you want to do it, it's not a big deal, but it doesn't matter which way you go. I just saved myself a division step.
Yeah, because I got to the second step after you took the derivative, and then I was like, there's no way I have to FOIL all this out.
But you could, and if you had to find more than one tangent line, that would probably be ineffective. If you had to find like 6 tangent lines,
Yeah.
I would want the closed form formula where I can just plug the x's and y's. Like I can type the equation in my calculator and just do like y1 of 2, y1 of 6, and like buzz through it a couple of times without having to do it over and over again. But if I just need to do it once, just plug the x and y in. And I don't imagine there would ever be a situation where you'd have to do it more than once, to be honest with you. Like, that'd be hard for me to foresee it. Because it'd just be like tedious for the sake of it being tedious. And nobody, this is tedious at times already. Like, I don't need to make it more tedious by doing something like that. Does that feel okay? Elena?
Number 9.
Uh-huh. This will be the last one before we start the new stuff. Is that all right with everybody?
Yes. We do 9 and 13.
You need to pick. Which one would you rather do?
Okay. I don't know. Okay.
Nine's way more.
Not 9.
Not if you do it the right way. It's not way longer.
Well, I don't get either, so I guess I'll do 9. I think.
So, who used product rules to do this?
Oh, wait,
I would not.
maybe that's why.
This is what I would start by doing, because that's super easy. And I still end up with some product rules, but feels like it's going to be nicer.
It should switch up.
Yep. And now I'm going to do the calculus. Product rule here. Product rule there. And now I'm going to move the dy dx's onto one side. So I'm going to subtract a 6xy dy dx, and then add a 3y squared dy dx. And then I'm going to subtract over a 5x to the fourth, a 4x cubed y, and then just divide both sides by x to the fourth minus 6xy plus 3x squared. And I think that'll do us. X to the fourth minus 6xy plus 3y squared.
Yeah.
Right? Because when I factor out the dy dx, that would be the coefficient on dy dx. I'm just trying to save myself having to write down like a trillion steps when it's like, I see to myself like, okay, that's what I need to do next. Why show the factoring and then the division if I can see what I need to divide already? Let me just divide it and just be done with it. You know what I'm saying? Trying not to take like an entire sheet of paper to do a problem because I'm writing down steps that I don't really need to write down. But if you need to write it down, then write it down, right? Some of these steps I'm just going to talk through what I did and then just do 2 or 3 steps at once because I'm confident I can do it correctly and I see what to do, and I might make some note or I might say aloud what it is that I'm doing, but I don't want to take, like a million lines to do this because sometimes it just like makes it easier to get caught in the weeds or whatever, Elaine, does that feel better? Not quite as bad as maybe it looked initially?
Yeah, I think I tried to, I don't even know what I tried.
Yeah, I think if you didn't FOIL that out, I think that's probably worse.
I did use product.
Because then there's product rules inside of product rules, and that gets complicated.
I got really confused. I tried using chain rule, it wasn't working.
Yeah. Yeah, so that's the way I would approach that. It just feels like it's going to be easier because then you have like dy dx's inside of dy dx's, and it just gets it potentially bad, right? Okay, or at least a lot to sort through. All right, let's look at 3.6. So here we're going to talk about taking the derivatives of logarithms. Let's actually do this proof because there's not a lot going on in this section other than this one rule. So to do that, we're gonna, not that. We're gonna start with, okay, let's say this. By the definition of a logarithm, I can say then a to the y is equal to x, right? this we can do the derivative of. So if I do the derivative of the left-hand side, what do I get? A to the y ln a times, what variable did we just differentiate? A is a constant. Y, and we differentiate with respect to x.
dy over dx.
There you go. And what's the derivative of x? So if I divide both sides by, okay, what do I want to do now? So I have this, yep, and then I can do dy dx equals 1 over a to the y, natural log of a. And what is a to the y equal to? X. So I can just replace that then with x ln a, which is what we're looking for. So what's the proof look like for this one? Right? So if we do the derivative, we have 1 over x to the ln of e. And what's the natural log of e? 1. And we're done. Because we just used the derivative rule that we just developed in the previous one. These two rules for differentiating logarithms, what should we do with these? Memorize them. This is a big memorization chapter. Emma. That's e, log base e of x. That's okay. Is that what you need? All right, from here on out, we're just practicing using these two rules. Yep. So let's say we want to do the derivative of y equals the natural log of x cubed plus 1. When we take the derivative of the left-hand side, what do we get? dy dx. Because we took the derivative of y. And to do the derivative of the natural log of x cubed, what do we need to use? Chain rule, yes, because we have stuff inside of the logarithm. So the derivative of the outside is going to be 1 over the insides. And then we have times the derivative of the insides. What's the derivative of the inside?
3x squared.
Good, so I have 3x squared over x cubed plus 1. And I'm done. And that's not bad, right?
Yeah.
Pretty easy chain rule. No big deal. So what is this? What are these things that I've written down? This is just those two logarithm rules written as chain rules, right? If I'm differentiating with respect to x and I have the log of some inner function u, I get 1 over u, that's the derivative of the outside, times du dx, that's the derivative of the inside. So this is nothing that you would need to memorize. This is just those two rules for logarithms that we just went through. written as chain rules. But like, dude, I know the chain rule, I know the logarithm rule. Why do I need to memorize this? You don't. Okay? You don't. That's all that's doing, though. You can if you'd like. I just, when the book does stuff like this and like highlights these things, I want to point out what is this that we're actually looking at. Sure. Let's look at the next example. Yes, Elena.
I know, like, so you kind of get away with thinking of the chain rules like F prime, G back, like G prime. Like, when you like, I don't, how does it go from being like 3 pieces to just 2 for outside and inside?
So here, like my f of x is the natural log of x, and my g of x is u. So when I do the derivative of the outside, or if I do the derivative of f of g of x, I get 1 over g of x times the derivative of g of x, and g of x is u. And when I take the derivative of u with respect to x, I get 1 du dx. Is that?
That makes sense.
Okay, so that's all that's saying. It's just like, all we're doing is just writing this as a chain rule applied to that derivative rule before. I don't know why you'd want to memorize like the two separate, like another separate thing when it's like, I already know the chain rule. I'm going to memorize this derivative rule. I know how to use the chain rule in conjunction with other derivative rules already. This is just another instance of me doing that. To me, it feels like more stuff to memorize I don't really need to memorize because I can just like, hey, I'm just going to learn how to use these things in combination because I'm already having to do that. But whatever approach you want to take. All right. Let's look at the derivative of the natural log of sine of x. When you look at this, what do you see? Chain rule. Great. So the outside function is? Okay, the derivative of the outside is 1 over sine x. Great. And the derivative of the inside is? So cosine over sine is cotangent. And that would be it. We haven't even gotten to the really nice stuff. It's going to get nicer.
Wow.
Yeah. Because here in a moment, I'm going to show you a shortcut for avoiding having to use like potentially like product chain quotient, like all kind of in conjunction with each other. And we can probably turn most of those instances into just a bunch of chain rules with some crappier algebra. So it's like kind of a 50-50 trade-off. But if it's a free response question, you can skip the algebra cleanup, and it can be messy, and that's okay. So yeah, it's potentially a quite useful technique we'll show you here in a few minutes. So here, differentiate the square root of the natural log of x. The outside is 1/2 ln of x to the negative 1/2. And the derivative of the inside is 1 over x. So if I wanted to clean this up, let's say 2x square root ln x, all in the denominator. Was okay with that? Okay. about this one here? Also a chain rule. So the derivative of the outside is
1 over 10 or 2 plus sin x.
times the natural log of 10. And the derivative of the outside is
Cosine x.
0 plus cosine x. So we just have cosine x over 2 plus sine x natural log of 10. Oops. Does that feel okay?
Is it inside? Or is that the outside?
This is the derivative of the outside, and this was the derivative of the inside.
Minus sign. Flip.
Yep. All right. Let's look at example 5. And
And,
another chain rule.
oh boy.
Or,
Ooh, I like or.
or
Or.
maybe I do some algebra first to make this easier.
That's not what
Who remembers their properties of logarithms?
I'm not.
There are 3.
Oh, the addition one to you?
The product, quotient, and power properties for logarithms
Isn't it like this?
state that log of AB is log of A plus log of B. Log of A over B is log of A minus log of B. And log of A to the B is B times log of A. So by applying these, I'm going to turn this into, instead of a chain rule, with a quotient rule inside of that, with a chain rule inside of that, into 3 standalone chain rules. Or I'm sorry, 2 standalone chain rules, even better. So what I'm going to do is I'm going to start by taking this and expanding this logarithm. So the order when expanding that I want to apply my properties is quotient to product to power. So do I see a quotient property in this logarithm? I do. So I can,
Matter that it's natural log instead of.
this could just be log base C, any C.
Oh,
So I can do that. And then do we see any product properties?
not particular.
No, I don't see anything multiplied together inside the logarithms. Do we see a power property?
Yeah. 1/2.
Though, good, the square root is the same as a power of 1/2. So I can do that. Wouldn't you rather differentiate this?
I would know.
If those 2 things are equal, let's just take the derivative of that stuff.
I mean, that's cheap.
That makes life much, much simpler. So if I do the derivative of this, when I do the derivative of natural log of x plus 1, I get times the derivative of x plus 1, which is just 1. Awesome. Then I'll have, when I do the derivative of negative 1/2 natural log of x minus 2, I get the minus still. I get the 1/2. And the derivative of natural log of x minus 2 is?
1 over.
And the derivative of the inside is? 1. So what do we have here?
1 over x plus 1 times 1 over 2x.
And then you could make a common denominator if you wanted to. I think this is fine for a final free response answer. If it was a multiple choice question, they might give you things with a common denominator. Yeah. But like, I can add two fractions at this stage of the game, right?
Can
I've taught all of you how to do this. Whether you can still do that right now, that's another question. But the answer is that you should be able to do this conceivably. So this, what we did right here, is a super helpful, right? If I see the log of a bunch of stuff, use your product quotient power properties to make the derivative mega simpler. A little bit of algebra in the beginning can save you a whole lot of calculus later on, right? That was turned into a pretty easy derivative where at first glance it was like, oh, boogers. Rita.
So you said for expanding it's like the orders.
Shh, I can't hear. What?
Oh, you said for like expanding it's like quotient product power.
Yes, that's the order in which you want to apply them.
Like compressing it, is it just the
Reverse order, yes. Although you would not probably want to compress to do a derivative because now you're making your derivative harder. Really, we're only going to be going the one-way expanding. Okay. So if I want to find the derivative of the natural log of the absolute value of x,
Is it one?
no, it's written right there. It's still 1 over x.
Wow. So close.
Are we not doing trips?
Well, I put the answer under example 6, right? We are going to do example 7, but I'm going to use it as an exercise to show you how to take this awful looking problem.
Yeah, this says.
And it does. Looks really nasty, right? Guess what I'm going to do? If you ask me, if I look at this, I see a quotient rule, I see a product rule, and I see 2 chain rules.
I don't know. I just see numbers. Yeah, I don't see anything. I see
Well, divided, right? When I do the derivative of the numerator,
I thought it was
that's multiplication, so that's a product. When I do the derivative of this piece, that requires a chain. When I do the derivative of that piece, it's going to require a chain. Yeah. How do I know that?
Yeah, like what?
Because I'm just looking from the inside out. So the first thing I need to do, since it's all a fraction, be the product rule. To do the product rule, I need to take the derivative of the numerator. That's a product. To do the derivative of that product, I'm going to require a chain rule to do that piece. The other part of the quotient rule requires me to do the derivative of the denominator. That requires a chain rule. That's just me kind of working through the, yes, go ahead, the big picture here. I am not going to do any of that to do this. Here's what I'm going to do. Yes, Chuchu. What? Here's what I'm going to do instead. Are you ready? I'm going to take the natural log of both sides. By doing that, what does that allow me to do? I can do the logarithmic properties. Excellent. So the first property we use is
Or quotient.
quotient. So I'll have the numerator minus the denominator. And then we're going to look for which property next? Okay. Do I see that?
Yes.
In the numerator, correct? Then we look for powers. And I see 3 of those. Everybody's okay there? Now I'm ready to differentiate. So if I start on the left-hand side, what's the derivative of the natural log of y?
1 over y.
1 over y dy dx.
Oh,
So it's because I'm differentiating with respect to x, not an x, I get a dy dx, and just the derivative of natural log of u is 1 over u, right? Okay, so then to do the derivative of 3/4 natural log of x, what do I get? Yep, or I'm just going to write it 3 over 4x. What do I get when I do the derivative of the 1/2 the natural log of x squared plus 2?
times dy. Wait, oh,
The derivative of the inside, right? And then the last one,
5 times 1.
3.
okay? I notice here that those 2's can cancel. Everybody's okay? But we want just dy dx, right? So what do we have to do to both sides to get just dy dx? Great. So dy dx is going to equal this stuff times y.
Where did you get the 3 for the 5 times 1 over 3 is equals to times 3? Where's the 3?
The derivative of the inside.
Oh.
So far, so good? And what's y? Y was the original problem, right? That was x to the 3/4 times, where I lost it here somewhere. There it was. X squared x squared plus 1 over 3x plus 2 to the 5th. And now you can see where the algebra kind of, the trade-off becomes. The calculus was pretty easy. The algebra now to clean that up stinks. But if this is a free response question where I don't need your fully simplified algebraic answer, you're done.
You can't stop backward, it was just y.
You cannot stop back where it's y, because you should have dy dx shouldn't really be in terms of x and y. It should really just be in terms of x's when at all possible. Now, if you're doing implicit differentiation, it's okay to have y's in it, but this was not an implicit differentiation problem, right? This was just a regular old derivative. You should have just x's in that. Jacob.
If we simplified it, easier to just multiply the y in and then plug it in afterward.
I would probably, if I was going to simplify this, make a common denominator here first, because now you're just multiplying two fractions together.
Yeah.
And if you can if you can reduce, then you can reduce. If not, it's just like numerators multiplied together, just like, three things multiplied together and denominators multiplied together. So it just, that's where I would go. But you don't need to do that here. But that's what I would do to simplify it algebraically, is I'd make a common denominator before I multiplied the y in, so I just have fraction times fraction, and that's easy to deal with.
Yeah.
Rather than like multiplying that thing, the y through, and having like fraction times fraction, fraction times fraction, and then making common denominator. It's just like, ugh.
Yeah.
Keep it simple. Easier to make a common denominator in that stuff I circled in yellow than it would be if I multiplied that extra y through, because it's just less writing. So this technique I've just shown you is logarithmic differentiation. What we do is we take the natural log of both sides and then use the laws of logarithms to simplify. Really, we mean expand. We differentiate implicitly then with respect to x and solve the resulting equation for the derivative, for y prime, or dy dx is really how we've written it. And then I have here to do the same problem with doing logarithmic differentiation, but we skipped doing it the dumb way already. So, not that it's a dumb way. There's nothing wrong with doing, you know, the quotient product in two chains. It just was like, it feels like this might be easier in a lot of cases. So what if we wanted to do this one to differentiate x to the square root x? You're not going to be able to do this as a chain rule.
Take the natural log.
Yeah, this has to be a logarithmic differentiation problem. And how do I expand that logarithm? I do the power property. It gives me the square root of x times the natural log of x, right?
How do you know it's the natural log?
You can pick any log you want, but why you'd pick anything other than the natural log, I don't know. Because when you do the derivative of the natural log, you get 1 over x instead of 1 over x times the natural log of a, which, like, I would never want to add in a bunch of extra constants if I didn't have to. If I have my choice, I'm picking natural log every single time. And now, if I want to do the derivative, 1 over y dy dx equals square root of x times 1 over x plus 1/2 x to the negative 1/2 natural log of x. And then we just multiply the y back over. So I have 1 over square root of x plus natural log x over 2 square roots of x. So I can call that 2 plus natural log of x over 2 square roots of x. And then we'll multiply times y. Yeah, we'll do it there. So I have dy dx equals 2 plus natural log of x over 2 square roots of x times x to the square root x.
Wait, how can you not that 1 second step? Does it just become square root of x over x?
Right here. So this is like my f, and that's like my g. So this is f g prime, and then f prime g.
Is that on the third step, is that equals?
Yeah. Yeah, just a messy equals.
The green and the
Rita?
But like, why can we do two on this?
Why can't you?
Yeah.
What's the outer function? Right?
I don't know.
Like that's why, right? Like what is the outer function? Is it a power of square root? Yeah, you have a variable in the as the base of the exponent, a variable in the exponent. Like what's the outer function? Because we don't have like the base. You can't do it as e to the x or a to the x because the base isn't a constant. But it's also not like a power rule because the exponent isn't constant. So it's not like x squared or x to the fifth or something. It's like, what derivative rule can I use on this? I don't have one. I have to do it as a logarithmic differentiation. It's not a silly question at all. But that's it for this section. It's basically just like these two new derivative rules and this new technique that you can use to deal with nasty derivatives that makes the calculus a little easier, but leaves you with like maybe more algebra cleanup than necessary at the end. So it's like a trade-off. But in the case of I don't need to I'm not looking for the simplest answer. It's a really useful technique. Now, if it's a multiple choice question, I might not go a logarithmic differentiation route because it might be harder to get a reasonably simplified answer to tell what choice I should make. It might be easier to go through and just do it as like just a hard calculus problem. Or it might not. It's like it's hard to tell often by looking at it. Elena? We are done.
Could we do number 15?
Yeah.
Just like the last five.
Sure, we can look at number 15. So we have 2 more sections in this chapter before test time, just FYI. Yes, of course.
What's the last Friday?
So we're gonna do this week. We'll do 7 on Thursday, and then Monday next week we'll do 10. And then we'll do a review day on Wednesday, and prospectively the test will be Friday next week. We'll have a conversation as it gets a little bit closer.
We should do it Tuesday.
I was about to say, let's
It's
get the
Halloween.
weekend.
Oh,
So-
wait, no, Halloween's next Tuesday.
So,
But
no.
still, never mind.
So it just,
That was the whole week.
so look, hold on guys. Look, as far as the test date goes, I'm fine with you guys to some extent picking the test date, and it can be later, but I would need to start the next chapter. So like once we've, you can save the review day for the class before the test, but in any extra days we're pushing out, I need to keep moving. Now that's not going to add more stuff to your test. Your test will still be fixed on the topics that are listed under test 3. And you guys can think on that because I know Halloween is coming and there's, you have your own social agendas to consider when trying to plan for this, and you may have other classes and other stuff going on too. And I'm okay with like moving dates around if I have the flexibility to continue moving forward as we're waiting and delaying. That's okay. I don't have any problem with that. So you think on that. Elena, you said you needed to see this one?
Yes.
Okay. So derivative of the left-hand side requires a chain rule. The outer function is e to the x. So that's just the derivative. And then times the derivative of the inside, which is a quotient rule. So I'm going to have the bottom times the derivative of the top minus the top times derivative of the bottom over the bottom squared. And then for the right-hand side, I have that. So if I multiply the e to the x through, I'd have y e to the xy minus x e to the xy dy dx over y squared equals 1 minus dy dx.
Why is it because like e to the x is always e to the x, it's body b? I just didn't know if you're supposed to drop it off the y.
So it's the outside is the e to the inside, right? So the derivative is just e to the insides,
Oh, okay.
right? I would multiply both sides by y squared now, because I got to get those dy dx's in the same place. So if I add y squared dy dx over, and then I subtract the y e to the x over y over, I can factor out the dy dx and then divide by the y squared minus x e to the x over y. And that should be my final answer there. I thinks.
Thank you.
Of course. So these last two sections of chapter 3, I think are your easiest two sections of chapter 3, because there's no new derivative rules coming. You've seen the last of your derivative rules.
Like forever?
I think so.
Oh.
You have some theorems and stuff, but these are all the shortcuts you're getting.
Oh, man.
Because, well, if you think about it, what other types of functions have you talked about out that we haven't seen how to do the derivative of? Nothing, right? Like we've done trigs, we've done inverse trigs, we've done logs, we've done exponentials, we've done polynomials, we've done radicals. You know, like you've done just general power functions like e to the square root 2 or 2 to the x to the square root 2. Like even that kind of stuff we know what to do with. Like we've done it all that you've seen.
I have a clarifying